If an asteroid the size of a 20-story building hits Earth, it could flatten an entire country. This stark warning comes from asteroid experts studying cosmic threats. In late 2024, we faced this reality when asteroid 2024 YR4 was discovered with a 3.1% chance of Earth impact, the highest probability ever recorded for an object of its size. Today, we'll show you what NASA wants you to understand about asteroid strikes. Our detailed simulation reveals how destruction unfolds when these space rocks hit our planet. You'll witness the shockwaves, thermal radiation creating fires, and climate-altering aftermath, plus the detection systems that spotted 2024 YR4 and defense technologies being developed. The discovery of 2024 YR4. What if the most dangerous asteroid ever detected was heading toward Earth right now? In late 2024, that nearly became reality. On December 27th, during a routine scan of the night sky, the Atlas telescope in Chile captured something unusual, a faint moving that didn't match any known celestial patterns. This that would soon become known as Asteroid 2024 YR4, and it would trigger one of the most intense periods of astronomical assessment in recent history. The automated detection algorithm flagged the object's unusual motion across successive image frames, prompting immediate follow-up observations. Like a silent alarm that only scientists could hear, the discovery set in motion a ticking clock that would count down the hours as astronomers raced to understand this potential threat. When astronomers first calculated the preliminary orbit of 2024 YR4, they faced the challenge of uncertainty that accompanies newly discovered asteroids. With just a few hours of observational data, the possible orbital paths formed a wide cloud of possibilities rather than a single line. Within 24 hours, something unusual happened. Instead of following the typical pattern where impact probabilities quickly drop to zero as more data arrives, 2024 YR4's calculations began to converge on a disturbing number. Additional observatories joined the tracking effort, and the impact probability settled at 3.1%. This figure represents something truly unprecedented in astronomical terms. For perspective, typical potentially hazardous asteroids register impact probabilities measured in millions or billions of a percent, making 2024 YR4's 3.1% figure alarmingly high, like jumping from a 1 in a billion chance to roughly 1 in 30. Scientists at NASA's Center for Near-Earth Object Studies and the European Space Agency's Near-Earth Object Coordination Center independently ran orbital simulations, both arriving at the same alarming conclusion. Their models showed 2024 YR4 would make an extremely close approach to Earth, with a significant chance it could strike our planet. The next question was size. How big was this potential impactor? Initial measurements placed 2024 YR4 between 131 and 295 feet in diameter. This uncertainty prompted an emergency observation request to the James Webb Space Telescope, which paused scheduled deep space observations to gather crucial infrared data. The Webb data allowed scientists to refine the size estimate to between 174 and 220 feet across, roughly the height of a 10-story building. This narrower range helped emergency planners model potential impact scenarios while astronomers continued tracking the object's path. With a high impact probability and concerning size, 2024 YR4 earned a rare designation on the Torino Impact Hazard Scale, Level 3. The Torino scale categorizes asteroid threats based on both probability and potential damage, running from 0 to 10. Level 3 indicates a close encounter with 1% or greater chance of collision capable of causing localized destruction. Most asteroids never rise above level 0, even temporarily. As tracking continued, scientists identified a potential impact corridor, the region where the asteroid might strike. This corridor stretched from the central Pacific Ocean across parts of Africa to Bangladesh, covering some of Earth's most densely populated regions. This identification triggered emergency assessment protocols established by the International Asteroid Warning Network. Space agencies worldwide mobilized their tracking resources. Military radar facilities normally used for satellite tracking were repurposed to help pinpoint 2024 YR4's exact trajectory. For nearly 72 hours, 2024 YR4 maintained its worrying impact probability. Officials began preliminary emergency planning, considering questions like, would evacuation notices be necessary? Which countries needed alerts? How much warning would populations have if impact probability increased? Planetary defense experts simulated what would happen if 2024 YR4 struck Earth. The results were sobering. An asteroid this size hitting at the typical velocity of 45,000 miles per hour would release energy equivalent to approximately 7.8 megatons of TNT, over 500 times more powerful than the Hiroshima bomb. A land impact would create a crater roughly half a mile wide and devastate an area the size of a major metropolitan region. Buildings would be flattened for miles in every direction. The thermal radiation and blast wave would cause widespread casualties and infrastructural damage requiring years to rebuild. An ocean impact would generate tsunami waves potentially reaching dozens of feet high along coastlines hundreds of miles away. Either scenario would constitute one of the most significant natural disasters in modern history. On the fourth day of tracking, new observations finally provided relief. As astronomical measurements accumulated, orbital calculations became increasingly precise, and the potential impact corridor began to narrow. Eventually, it shifted entirely away from Earth, with the asteroid now predicted to miss our planet by approximately 280,000 miles, slightly further than the distance to the Moon. The 2024 YR4 incident lasted less than a week from discovery to all clear, but served as a critical stress test for our planetary defense systems. It demonstrated both the capabilities of our detection network and the uncomfortable gaps that still exist. The asteroid was only discovered 11 days before its closest approach, barely enough time to coordinate observations, let alone mount any deflection mission had it been on a collision course. The incident raised urgent questions about our preparedness. What if 2024 YR4 had maintained its collision course? What if it had been discovered even later? What if it had approached from the direction of the sun, where our detection capabilities are weakest? These questions highlight the importance of improving our asteroid tracking capabilities. Current telescopes scan the sky nightly, but can only detect a fraction of potentially hazardous objects, particularly smaller ones that could still cause regional catastrophes. Asteroids like 2024 YR4 represent a unique type of natural disaster, one that is both potentially catastrophic and entirely preventable with sufficient warning. Unlike earthquakes or hurricanes, asteroid impacts can be predicted years in advance if objects are discovered early enough, opening the possibility of deflection. Detection systems, our first line of defense. That advanced warning system sounds reassuring until you consider the sobering reality. An asteroid approaching from the direction of the sun would remain completely invisible until just hours before impact. This fundamental blind spot represents perhaps our greatest vulnerability in protecting Earth from cosmic threats. While deflection technologies continue to advance, they're essentially useless without sufficient warning time. Our planetary defense network relies primarily on ground-based telescopes like the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network strategically positioned around the globe to maximize sky coverage. These systems scan vast sections of the night sky, searching for objects that move against the backdrop of stars. When ATLAS detected 2024 YR4 from its remotely operated telescope in Chile, it was functioning exactly as designed, identifying a potential threat through automated observation protocols. What makes ATLAS valuable is its wide-field telescopes, capable of capturing large portions of the sky simultaneously. This design philosophy prioritizes breadth over depth, scanning the entire visible sky multiple times each night rather than focusing intensely on smaller regions. The trade-off provides greater coverage, but limits the system's ability to detect the smallest or most distant objects. Still, This approach effectively identifies objects large enough to cause regional damage before they reach Earth. The designation process reveals much about how astronomical discoveries are cataloged. When 2024 YR4 was first spotted, the Minor Planet Center assigned its provisional designation following established conventions. 2024 indicating the year of discovery, Y signifying the second half of December, and R4 denoting it was the 117th provisional designation assigned during that period. This standardized naming system allows astronomers worldwide to reference the same object with precision during urgent assessment periods. Despite these sophisticated systems, our detection capabilities have significant limitations. The most concerning is this sunward blind spot, like a cosmic blindfold that prevents optical telescopes from observing objects approaching from the direction of the sun due to overwhelming glare. The 2019 close approach of Asteroid 2019 OK demonstrated this vulnerability perfectly. It wasn't detected until just hours before passing Earth at lunar distance because it approached from our daytime side. An asteroid taking this approach path might remain undetected until it's already hours away from Earth, rendering our deflection capabilities useless. The European Space Agency's Near-Earth Object Coordination Center monitors over 37,000 known near-Earth asteroids. Current estimates suggest nearly 70% of potentially hazardous asteroids smaller than 140 meters remain completely invisible to our detection systems. These mid-sized objects are large enough to devastate entire cities, but small enough to evade detection until they're dangerously close. To expand our detection capabilities, the ESA is developing new telescopes like the FLY system. These instruments will autonomously scan the night sky and alert astronomers to potential new asteroid discoveries by the following morning. This represents a crucial step toward addressing our current blind spots, though the fundamental limitation of Earth-based optical telescopes will persist without space-based alternatives. When a potential threat like 2024 YR4 is detected, astronomers immediately begin calculating its orbit based on successive observations. This process involves complex mathematical modeling that considers the object's position at different points in time, allowing scientists to project its future path and assess whether it might intersect with Earth. These initial calculations contain significant uncertainty, which explains why impact probabilities often increase before eventually decreasing as more data becomes available. The uncertainty regions in orbital calculations appear as an elongated ellipse encompassing all possible positions where the asteroid might be at a given time. With each new observation, this ellipse shrinks as the asteroid's position becomes better constrained. For objects that will ultimately miss Earth, the uncertainty region often contracts in a way that initially seems to increase the impact probability before definitively ruling out a collision. This explains why potentially threatening asteroids frequently make headlines before being downgraded to non-threats days later. The James Webb Space Telescope represents another valuable tool in our detection arsenal, though not primarily for discovery. Webb's infrared capabilities allow for more precise characterization, particularly size estimation through thermal imaging. When Webb observed 2024 YR4, it substantially reduced uncertainty about the asteroid's dimensions, providing crucial data for impact risk assessment. Space-based detection systems offer a potential solution to the sunward blind spot problem. A telescope positioned at the L1 Lagrange point between Earth and the Sun could observe the region currently hidden from Earth-based telescopes. Similarly, systems in Venus-like orbits could provide complementary perspectives, creating a more comprehensive detection network. These concepts remain largely theoretical due to funding constraints, though the modest cost compared to the potential damage of an undetected impact makes them compelling investment opportunities. The current detection paradigm prioritizes larger objects, those capable of causing global catastrophe, while accepting greater risk from smaller impactors. Asteroids larger than 1 kilometer have been cataloged with approximately 95% completeness, while the vast majority of 50 to 140 meter objects remain undiscovered. This approach reflects both technical limitations and resource constraints, but leaves Earth vulnerable to city-destroying impacts with minimal warning. For asteroids detected with sufficient lead time, our tracking capabilities improve dramatically over subsequent observations. Radar systems like those at Goldstone Solar System Radar Facility can precisely measure an asteroid's position, velocity, rotation, and surface features once it comes within range. These detailed observations can reduce orbital uncertainty by orders of magnitude, allowing for definitive assessment of impact risk. The ultimate goal of these detection systems is to provide sufficient warning time for deflection missions. Current technology would require years of advance notice to successfully alter an asteroid's trajectory enough to prevent impact. This long lead time is necessary because the required course change is minimal if applied far in advance, but becomes exponentially more difficult as the asteroid approaches Earth. The first 10 minutes after impact. Those decades of warning time become irrelevant once the clock hits zero. At 45,000 miles per hour, a 200-foot asteroid transitions from being a distant threat to unleashing more destructive energy than multiple nuclear weapons in less time than it takes to brew coffee. Let's imagine a scenario where an asteroid the size of 2024 YR-4 strikes a major metropolitan area without warning. Our simulation begins at the moment of impact, a moment that transforms an ordinary day into the beginning of a catastrophe unfolding in horrifying precision. In the first 60 seconds, the asteroid makes contact with Earth's surface. The kinetic energy of this cosmic projectile instantly converts to heat and pressure as it slams into the ground. The initial impact produces a blinding flash that outshines the sun itself. An overwhelming pulse of light temporarily blinds anyone looking in its direction for miles around. The asteroid compresses under the extraordinary pressures of impact and vaporizes in a fraction of a second. This rapid phase change releases an enormous amount of energy, creating temperatures exceeding those on the sun's surface. Anyone within several miles experiences this as an overwhelming sensory assault. A flash of light followed by intense heat washing over them like a solar furnace door thrown open at point-blank range. As we move into minutes 2 and 3, the violence of the impact reshapes the landscape. The ground yields to forces it was never designed to withstand. An impact crater forms where city blocks, transit stations, or shopping centers once stood. Surrounding this newly formed crater, the Earth buckles and deforms. Rock from the impact site gets ejected skyward at supersonic speeds, traveling miles into the atmosphere before beginning its deadly return. The familiar skyline vanishes, replaced by an expanding cloud of debris and dust climbing rapidly upward. Between minutes 3 and 5, the destruction expands in multiple deadly forms. Thermal radiation from the superheated impact zone ignites everything flammable within a 5-mile radius. Countless fires erupt simultaneously as the intense heat consumes buildings, vehicles, and vegetation. These scattered blazes merge, potentially forming a massive urban firestorm if sufficient combustible material exists. Simultaneously, a physical shockwave propagates outward from the impact point, faster than sound itself. This wall of compressed air carries tremendous pressure that maintains its destructive power across great distances. Buildings, trees, and infrastructure become obstacles to be flattened rather than structures that can resist. As we reach minutes 5 through 7, the shockwave continues outward, devastating areas seemingly safe from the impact. Buildings up to 15 miles from ground zero face forces beyond their design tolerances. Modern skyscrapers sway past their structural limits. Older buildings simply collapse. The shockwave applies its physics equally to hospitals, schools, homes, and factories alike. Even at 30 miles from impact, windows shatter in a synchronized chorus of destruction. The air fills with high-velocity glass shards, causing numerous injuries far from ground zero. Those sheltering indoors now face dangers from their compromised surroundings. In minutes 7 through 10, secondary effects begin their own destructive sequences. The initial ejecta, material thrown skyward in the first moments, rains back down across a wide area. Some fragments start new fires where they land, while the impact triggers seismic activity equivalent to a magnitude 6.0 earthquake. Unlike natural earthquakes originating deep underground, this event begins at the surface and creates unusual wave patterns that damage infrastructure untouched by the blast. Underground utilities rupture, gas lines break, and water mains burst, adding flooding and gas explosions to the catastrophe. Dust clouds rise and spread, reducing visibility and creating immediate respiratory hazards. The finest particles begin their journey into the upper atmosphere, where they'll eventually cause short-term climate effects extending beyond the impact region. Asteroid impacts layer multiple destructive mechanisms simultaneously. The pattern varies based on several factors. The asteroid's approach angle creates asymmetrical damage, typically more severe along the incoming trajectory. Its composition matters. A dense metallic object delivers different effects than a loosely packed rubble pile. And the impact location's geology plays a crucial role, as striking granite produces different patterns than hitting sedimentary layers. For coastal impacts, the devastation grows more complex. Beyond immediate blast effects, the impact displaces enormous water volumes, creating tsunami waves traveling hundreds of miles. These waves reach coastlines hours later, bringing destruction to regions that might have thought themselves safe. Aerothermal effects dominate the destruction pattern, accounting for over 60% of casualties from asteroids up to 400 meters in diameter. Thermal radiation causes approximately 30% of losses, while ocean impacts shift this profile dramatically, with tsunami effects accounting for 70 to 80% of casualties, depending on asteroid size. What will the first 10 minutes after an asteroid impact look like? A rapidly expanding circle of total devastation measured in miles, surrounded by widening rings of decreasing but still deadly damage. Thermal radiation transforms urban landscapes into massive fire zones. Shockwaves topple structures and shatter windows far beyond the immediate impact. All of this unfolds with a terrifying rapidity that gives victims no time to process what's happening, much less respond. Effectively, like watching a year's worth of natural disasters compressed into mere minutes, with no warning and no escape. Near misses closer than we knew. The disaster scenarios we've explored aren't just theoretical models confined to computer simulations. Earth has experienced several alarming close encounters with asteroids that went almost entirely unnoticed until they had already passed. In 2019, a city-killer asteroid large enough to flatten a metropolitan area silently slipped past our planet at just 1/5 the distance to the moon, and astronomers detected it merely hours before its closest approach. February 15th, 2013 began as an ordinary winter day in Chelyabinsk, Russia. Dashcam videos later showed an intensely bright light streaking across the morning sky, brighter than the sun itself. A 20-meter asteroid, roughly the size of a 6-story building, exploded in the air above the city with absolutely no advance warning. The resulting airburst released energy equivalent to about 440 kilotons of TNT, approximately 30 times more powerful than the atomic bomb dropped on Hiroshima. The shockwave shattered windows throughout the city, sending glass flying through homes, schools, and businesses. More than 1,500 people sought medical attention, primarily for injuries from flying glass and debris. Buildings sustained structural damage across a wide area. Yet this represented a relatively small asteroid by cosmic standards, one that disintegrated before even reaching Earth's surface. What makes the Chelyabinsk event particularly sobering is what it revealed about our detection capabilities. Despite our network of telescopes scanning the skies, no one saw this asteroid coming. Not a single observatory or tracking system detected it before impact. The asteroid approached from the direction of the sun, effectively blinding our ground-based telescopes until the moment of atmospheric entry. A critical blind spot in our planetary defense that continues to concern astronomers today. On July 25, 2019, asteroid 2019 OK passed alarmingly close to Earth, approximately 45,000 miles away, roughly one-fifth the distance to the Moon. This space rock, estimated to be between 57 and 131 meters wide, could have caused devastating regional damage had its trajectory been slightly different. The most troubling aspect? Astronomers discovered it just hours before its closest approach. This substantial asteroid could potentially wipe out an entire metropolitan area. Yet our detection systems picked it up only at the last possible moment. Had it been on a collision course, we would have had virtually no time to evacuate vulnerable areas. Then in 2020, another asteroid broke records for its extremely close approach. This object passed within just 1,830 miles of Earth's surface, the closest non-impacting approach ever recorded. For perspective, many of our weather and communication satellites orbit at higher altitudes than this asteroid's pass. Had it been slightly larger or on a different trajectory, the outcome could have been catastrophic. What's most concerning about these incidents is how they revealed critical gaps in our early warning capabilities. In many cases, astronomers only detected these objects after they had already passed Earth, a chilling reminder of our vulnerability. This post-passage discovery pattern highlights a troubling reality. We're often learning about potential threats only after we've already dodged them, leaving our safety to cosmic chance rather than preparedness. The challenges in detecting incoming asteroids are numerous. Objects approaching from the sun's direction remain effectively invisible until they've moved out of the sun's glare. Smaller asteroids only become visible when they're already quite close to Earth. And our current detection networks, while improving, still have significant blind spots and coverage gaps. The Atlas system that discovered asteroid 2024 YR4 represents a significant improvement in our detection capabilities, but even this sophisticated network can miss objects approaching from certain angles or moving at unexpected speeds. The ongoing discovery of near-Earth objects reveals how frequently Earth experiences close calls that simply weren't observed in previous decades due to technological limitations. Consider asteroid 2024 YR4, first spotted on December 27, 2024. It had already made its close approach to Earth 2 days earlier, passing at a distance of 828,800 kilometers. Despite being between 40 and 90 meters wide, roughly the size of a 10-story building and comparable to the asteroid that caused the 1908 Tunguska event, it wasn't detected until after its closest approach. These discovery patterns reveal an uncomfortable truth. Earth regularly experiences close brushes with potentially hazardous asteroids that go undetected until they've passed. As detection technology improves, we're finding more near-Earth objects. In reality, these objects have always been passing near our planet. We just lack the technology to observe them. The identification of potential future impacts provides a crucial window for preparation. Take asteroid 2024 YR4. Automated warning systems identified a small chance of impact in 2032, prompting immediate action from international asteroid response groups. This early warning represents what astronomers hope to achieve for all potentially hazardous objects, but they can only warn us about objects they've actually detected. What's particularly sobering is how many similar objects might have passed Earth throughout human history without anyone noticing. Before modern astronomy and automated survey telescopes, countless asteroids likely passed at similar distances with absolutely no human awareness. Our recent discoveries are revealing the cosmic shooting gallery Earth has always traveled through. For every asteroid we detect, many more likely pass unobserved. Astronomers estimate we've discovered only a fraction of potentially dangerous near-Earth objects, particularly those in the smaller size ranges that could still cause significant regional damage. The James Webb Space Telescope's planned observation of asteroid 2024 YR4 highlights how seriously astronomers take these potential threats. Using our most advanced space telescope demonstrates the priority scientists place on refining our understanding of these objects' orbits, compositions, and characteristics. A race against time to protect
Ocean
our
impact,
vulnerable planet
the tsunami
from future
threat.
close encounters.
Earth's
that
vast
might not
oceans
miss.
aren't
just a shield against cosmic impacts. They're an amplifier. When an asteroid strikes water instead of land, the energy transfer creates something far deadlier than a crater. A chain reaction of megatsunamis that could simultaneously devastate coastal cities across entire continents. The statistical reality makes this scenario particularly concerning. Nearly 72% of our planet's surface is covered by water, meaning that most asteroid impacts throughout Earth's history have likely occurred in oceans. This high probability transforms our understanding of asteroid threat assessment. While we often focus on direct strikes to populated areas, the more likely scenario involves an impact far from shore that triggers devastating secondary effects, reaching densely populated coastlines worldwide. Consider what happens in those critical first moments when an asteroid plunges into open water. The kinetic energy transfer is immediate and catastrophic. Upon impact, the asteroid vaporizes an enormous volume of seawater, creating a temporary cavity spanning several miles in width. A momentary void in the ocean itself, a violent displacement of water on a scale difficult to comprehend. What follows obeys simple but terrifying physics. The surrounding ocean rushes to fill this cavity with incredible force. As water collapses back into this void, it creates a central column rising high above the surface, a temporary mountain of water that becomes the genesis point for tsunami waves. These waves propagate outward in all directions like ripples in a pond, but carrying cataclysmic energy, an ocean transformed into a spreading circle of destruction. Asteroid-generated tsunamis differ fundamentally from those caused by underwater earthquakes. Their energy distribution, wavelength patterns, and propagation characteristics create waves with unique properties. While earthquake tsunamis typically generate longer wavelengths, asteroid-induced tsunamis produce more complex wave patterns with different energy concentrations, affecting both wave travel and shoreline behavior. Near the impact zone, initial waves could tower hundreds of feet high, walls of water moving with unstoppable momentum. While diminishing with distance, these waves maintain devastating power hundreds of miles away. Coastal areas could face tsunami waves tens of feet high, overwhelming seawalls and flooding far inland. When these massive waves approach coastlines, the shallowing seafloor causes them to slow but grow taller through shoaling. Narrow bays, inlets, and V-shaped harbors can amplify wave heights further, channeling the tsunami's energy into even more destructive forms. Some coastal configurations might experience wave heights several times greater than nearby areas due to these amplification effects, turning natural harbors into funnels of concentrated destruction. The inundation zones would be extensive, with water reaching miles inland in some locations. Low-lying coastal plains would be particularly vulnerable. Even in cities with varied elevation, these waves would force water up slopes and through urban corridors, creating high-velocity flows capable of destroying structures not designed for such forces. Buildings that might withstand hurricane winds could be completely overwhelmed by the mass and momentum of tsunami waters. This scenario is particularly insidious because coastal regions house a disproportionate percentage of the global population. 8 of the world's 10 largest cities are coastal, and approximately 40% of people worldwide live within 60 miles of a coastline. While a land impact might demolish one metropolitan area, an ocean impact could simultaneously affect dozens of coastal cities across multiple continents. Direct impact consequences. The immediate physical damage would be catastrophic. Structures closest to shorelines would be obliterated by the initial wave force. Further inland, buildings would be damaged by water pressure, debris impacts, and scouring as waters receded. Underground infrastructure, subways, utility tunnels, parking structures will become deadly traps filled with fast-moving water. Saltwater intrusion would immediately contaminate freshwater supplies, creating public health emergencies. Municipal water systems, agricultural lands, and natural aquifers could all become compromised, necessitating massive relocation efforts and emergency water distribution. Secondary effects. Port infrastructure would suffer catastrophic damage, disrupting global supply chains. With approximately 90% of world trade traveling by sea, the simultaneous destruction of multiple major ports would create economic shockwaves worldwide. Even undamaged ports might become unusable due to underwater debris or shifted seafloor topography. Economic consequences would extend beyond rebuilding costs. Tourism-dependent coastal economies would collapse. Insurance markets would face unprecedented claims, potentially triggering financial system instability. Property values in coastal areas would plummet, creating wealth destruction on a massive scale and potentially triggering a severe global recession. Emergency response systems would be overwhelmed by the geographic scale of the disaster. Unlike localized disasters allowing resource concentration, an ocean impact tsunami would require simultaneous rescue operations across thousands of miles of coastline. Aid organizations would face impossible decisions about resource allocation, with adequate supplies unlikely to reach all affected areas quickly. The recovery timeline would extend far beyond initial emergency operations. Rebuilding coastal infrastructure while implementing stronger tsunami protections would require years. Some severely damaged areas might never recover, creating permanent changes to coastal population distributions and economic patterns. This scenario presents a unique challenge for international coordination. While the impact might occur in international waters, the consequences would affect numerous nations simultaneously. Current disaster response frameworks simply aren't designed for catastrophes of this magnitude and geographic spread. Mitigation strategies do exist, but require advanced warning and effective communication. Communities with established tsunami warning networks and evacuation protocols would fare better. Vertical evacuation structures, buildings designed to withstand tsunami forces and provide refuge above wave heights, could save countless lives in densely populated areas where inland evacuation is impractical. Threat assessment, calculating real risk. While coastal communities rely on early warnings for tsunami evacuation, astronomers face a more fundamental challenge: determining which rocks hurtling through space actually threaten Earth in the first place. When a new asteroid appears in our telescopes, scientists don't immediately know if it's harmless or heading straight for us. And the math behind these calculations reveals a counterintuitive truth about cosmic risk assessment. At NASA's Center for Near-Earth Object Studies, located at the Jet Propulsion Laboratory, a complex system of mathematical calculations transforms limited observations into meaningful risk assessments. The moment a telescope captures a new asteroid, the object is entered into monitoring databases like NASA's Sentry system. This automated hazard monitoring system continuously scans the catalog of known near-Earth asteroids, calculating their orbits and assessing potential future Earth impacts decades into the future. These initial calculations are based on remarkably sparse data, sometimes just a handful of position measurements taken hours apart. From these few data points, astronomers must project an asteroid's future path through the solar system, accounting for the gravitational influence of the Sun, Earth, and other planets. The limited initial observations create what scientists call an uncertainty region, essentially a cloud of possible locations where the asteroid might actually be. This uncertainty region is critical to understanding impact probabilities. Rather than a single predicted path, the asteroid's orbit is represented by thousands of possible trajectories, each slightly different, but all consistent with the limited observations available. Some of these potential paths might intersect with Earth, while most will miss us entirely. The percentage of calculated paths that result in an Earth impact becomes the initial impact probability, like finding a needle in a cosmic haystack, where the needle represents potential Earth-crossing paths. What confuses the public is that as more observations come in, this probability often rides a roller coaster of cosmic fate, temporarily increasing before eventually dropping to zero for non-threatening asteroids. This behavior has a logical explanation. As the uncertainty region shrinks with additional data, The possible trajectories narrow. If Earth happens to be within this narrowing region, the percentage of calculated paths crossing our planet can increase, even while the absolute number of potential impact trajectories decreases. Each new observation shrinks the uncertainty region, much like how additional clues help detectives narrow their search area. For asteroids that truly pose no threat, continued observations eventually rule out all potential Earth-crossing paths, dropping the impact probability to zero. This pattern explains why initial alarming headlines often give way to all-clear announcements days later. To communicate these complex probabilities meaningfully, astronomers rely on two specialized risk assessment tools. The Torino scale offers a straightforward 0 to 10 rating system designed primarily for public communication. A rating of 0 indicates virtually no chance of collision or an object too small to penetrate Earth's atmosphere, while 10 represents a certain global catastrophe. This scale helps prevent unnecessary public alarm by providing context for news reports about newly discovered asteroids. For more technical assessment, scientists prefer the logarithmic Palermo scale, which compares the specific threat posed by an asteroid to the background level of risk from all known near-Earth objects. By incorporating the impact probability, object size, and potential energy release, the Palermo scale provides critical context for specialists evaluating each new discovery. The International Asteroid Warning Network, IWN, coordinates these assessments globally, connecting space agencies and astronomical institutions worldwide. This collaborative structure ensures potential threats receive comprehensive scrutiny from diverse observatories and analysis teams, as demonstrated during scenarios like Asteroid 2024 YR4. Size estimation adds another challenge to threat assessment. Unlike orbit calculations that benefit from precise position measurements, size estimates depend on more difficult brightness observations. An asteroid's apparent brightness depends on several variables: its size, reflectivity, rotation, and shape. Initial size ranges often span factor of 2 uncertainties, gradually narrowing as these properties become better constrained. This size uncertainty directly impacts risk assessment, as potential damage scales dramatically with an asteroid's dimensions. An object 100 meters across contains roughly 8 times more mass than one 50 meters in diameter, representing a significantly greater threat. As an asteroid's orbit becomes better defined, possible Earth-crossing paths narrow to specific geographic regions called impact corridors, bands across Earth's surface where the asteroid might strike. For asteroids with significant impact probabilities, these corridors help emergency management agencies understand regional risk. Keyhole passages represent one of the most sophisticated aspects of asteroid threat assessment. These narrow regions in space, if passed through by an asteroid during a close approach, can alter its trajectory due to Earth's gravity and potentially set it up for a collision during a subsequent encounter years later. Identifying these keyhole regions requires extraordinarily precise orbital calculations that look beyond immediate threats to future encounters. The entire threat assessment system combines observational astronomy, orbital mechanics, impact physics, and international cooperation to provide crucial advance warning of potential cosmic hazards. This warning time, whether days, months, or years, becomes the essential foundation for any defensive actions Earth might take against an incoming asteroid. Planetary defense, technologies to save Earth. This advanced warning system gives us time, but time for what exactly? When NASA deliberately slammed a refrigerator-sized spacecraft into an asteroid in 2022, they were rehearsing humanity's first line of defense against cosmic extinction. The DART mission made history as our first real attempt to change an asteroid's path. This wasn't a Hollywood scenario with doomsday countdowns and last-minute heroics. Instead, the Johns Hopkins University Applied Physics Laboratory managed a carefully calculated cosmic collision that would prove whether we could actually alter the course of an incoming space rock. The target was carefully chosen, Dimorphos, a small moonlet orbiting the larger asteroid Didymos. This binary system provided the perfect natural laboratory. By crashing the spacecraft into the smaller body, scientists could precisely measure any orbital changes by timing how long it took Dimorphos to circle its parent asteroid. The beauty of this approach was that neither asteroid posed any threat to Earth, creating a safe testing ground for planetary defense. When DART made impact, the results exceeded expectations. The collision altered Dimorphos' orbit by a full 32 minutes, a substantial shift that conclusively demonstrated kinetic impactors could work. The impact represented a significant change in trajectory that, if scaled appropriately, could divert a threatening asteroid from an Earth collision course. This achievement rewrote humanity's future, transforming us from passive observers of cosmic threats to active defenders of our planet. For the first time in Earth's history, humans deliberately altered the course of a celestial object, proving we need not share the dinosaurs' fate when facing celestial threats. The success earned widespread recognition in the scientific community. The DART team received both the 2024 Space Systems Award from the American Institute of Aeronautics and Astronautics and the prestigious Smithsonian Michael Collins Trophy for current achievement. These accolades underscored the mission's groundbreaking contribution to planetary defense strategy. Our planetary defense toolkit now contains several distinct technologies, each with unique advantages. Kinetic impactors like DART operate by direct collision, transferring momentum to alter an asteroid's path. They require years of advance warning, but use relatively simple technology that we've now proven effective. In contrast, gravity tractors offer precision without contact. These spacecraft hover near an asteroid, using their own mass to gradually pull the asteroid off course through gravitational attraction. While requiring decades of lead time, they provide exquisite control without risking fragmentation. Alternatively, for scenarios with less warning time or larger threatening objects, nuclear standoff detonations present a more powerful option. Rather than splitting the asteroid, a nuclear device detonated at a calculated distance creates radiation pressure that heats one side of the asteroid surface. The vaporizing material creates thrust, altering the asteroid's trajectory with significantly more force than other methods. For precise, sustained intervention, laser ablation focuses concentrated light beams on portions of an asteroid surface. As the heated material vaporizes, it generates thrust similar to a rocket engine, gradually pushing the asteroid onto a different path. This approach allows continuous adjustments over extended periods. Each defense method demands different lead times. Kinetic impactors need years for spacecraft construction, launch, and travel before impact can meaningfully alter a trajectory. The farther from Earth the intercept occurs, the less force needed to ensure a miss. Gravity tractors require decades of operation to sufficiently alter an asteroid's course. Their gentle influence makes them unsuitable for newly discovered threats, but excellent for managing known hazards with distant future impact possibilities. The nuclear option remains humanity's only viable solution for larger objects or scenarios, with warning times measured in months rather than years. The immense energy release can create significant velocity changes even with minimal lead time, though international treaty considerations complicate deployment. The effectiveness of any deflection attempt faces a critical variable: asteroid composition and structure. Some asteroids are solid monoliths, while others are essentially rubble piles loosely held together by gravity. DART's impact illustrated this challenge, creating an unexpected plume of ejected material that amplified the momentum transfer. While this worked in our favor during the test, it highlights how asteroid material properties significantly affect deflection outcomes. The scientific benefits extend beyond defense. 5 new papers in Nature Communications have revealed insights about the structure and origins of the Didymos-Dimorphos system, demonstrating how defense missions simultaneously advance fundamental knowledge. Our defense capability ultimately depends on warning time. With decades of notice, multiple options become viable, including reconnaissance missions followed by precisely calculated deflection attempts. With years, kinetic impactors remain feasible. As warning time shrinks to months, our options narrow dramatically. This time factor underscores why detection systems represent the foundation of planetary defense. More advanced warning means more available options and less force needed to avert disaster. A tiny nudge applied years in advance can ensure an asteroid misses Earth by thousands of miles, while last-minute interventions require enormous energy and carry greater risks. The DART mission's success has transformed asteroid defense from theoretical to practical. We now have demonstrated technology that could, with sufficient warning, protect Earth from certain impact threats. But it also highlights our current limitations and the importance of continued investment in both detection and deflection technologies. The question isn't whether we can deflect asteroids. DART proved we can. The questions now focus on scaling these approaches to different threat sizes, improving early detection, and developing complementary technologies to address the full spectrum of potential impact scenarios. Global collaboration, our collective defense. Defending Earth transcends national interests and political rivalries. Within 24 hours of discovering a dangerous asteroid trajectory, a carefully orchestrated international protocol activates that might determine humanity's survival. While we've explored technologies that could deflect incoming asteroids, the question of who makes these decisions and coordinates global response efforts reveals perhaps the most remarkable achievement in planetary defense. The United Nations formalized this collaborative approach in 2014 by establishing two critical international bodies that form Earth's cosmic shield: the International Asteroid Warning Network, IWN, and the Space Mission Planning Advisory Group, SMPAG. IWN focuses on detection and characterization, answering what's coming and how dangerous is it, while SMPAG handles planning potential mitigation missions, addressing what can we do about it. This division creates a comprehensive protection framework. IWN consolidates observational data from astronomical institutions worldwide, enabling accurate orbit determinations and impact probability calculations. SMPAG evaluates deflection options based on specific threat scenarios, weighing factors like lead time, asteroid composition, and technological readiness. The real-world test of this system came with Asteroid 2024 YR4. On January 29, 2025, IWN issued a potential asteroid impact notification, mobilizing the global astronomical community to gather additional data. Simultaneously, SMPAG convened to assess mitigation strategies, though further observations would later show the asteroid posed no actual threat. This response demonstrated how these organizations transform plans into coordinated action when facing potential cosmic hazards. The United Nations Office for Outer Space Affairs, UNUSA, provides the diplomatic foundation for this international cooperation. In April 2023, UNUSA hosted the 8th IAA Planetary Defense Conference, bringing together experts worldwide to advance asteroid defense strategies. During this conference, the White House Office of Science and Technology Policy released an updated national preparedness strategy with 6 key goals for enhancing the United States' ability to mitigate hazardous NEO impacts over the next decade. This global shield leverages each space agency's unique strengths in a united front against cosmic threats. NASA contributes its extensive detection network and technological expertise. The European Space Agency offers sophisticated risk assessment systems through its Near-Earth Object Coordination Center. Japan's Space Agency provides valuable characterization capabilities. Emerging space programs in countries like India and China add crucial monitoring coverage across different parts of the globe, ensuring no single point of failure exists in our planetary defense system. Communication protocols represent another critical element of this global collaboration. When identifying potential threats, IWN coordinates information dissemination to governments through established channels. These protocols ensure accurate information reaches decision-makers quickly, preventing both unnecessary panic and dangerous complacency. The experience with 2024 YR4 highlighted both the effectiveness of these systems and areas needing improvement, particularly in communicating complex probability assessments to non-scientific audiences. Looking toward the future, the European Space Agency has endorsed the United Nations designation of 2029 as the International Year of Asteroid Awareness and Planetary Defense. This initiative aims to strengthen global partnerships, educate the public, and include developing nations in defense strategies. The timing coincides with asteroid Apophis' close approach within 20,000 miles of Earth, closer than some satellites, providing an opportunity to test observation and communication systems. Despite these promising developments, significant challenges remain. Funding disparities between space agencies create uneven capabilities, with some countries deploying advanced detection systems, while others struggle to maintain basic astronomical infrastructure. Political tensions occasionally complicate information sharing, and consensus building around potential deflection missions, especially those involving nuclear options, remains contentious. Coordinating a deflection mission presents complex questions. Who would launch the mission? Which countries would provide funding? What technologies will be deployed? These questions necessitate diplomatic frameworks established before any crisis occurs. Currently, SMPAG is developing protocols to address these challenges, but many political and legal hurdles remain unresolved. Another challenge involves bringing developing nations into the planetary defense framework. While major space agencies lead current efforts, a global threat requires global participation. Programs are underway to help developing countries establish modest but valuable observation capabilities, ensuring asteroid defense benefits from diverse geographical coverage and builds worldwide scientific capacity. The 2024 YR4 experience provided valuable insights for improving international collaboration. Experts at NASA and partner institutions used this close approach to test notification processes and scientific assessment procedures. The lessons are being incorporated into revised protocols, with particular attention to streamlining decision-making processes and clarifying chains of command during potential emergency scenarios. Transparency remains a cornerstone of international asteroid defense efforts. NASA's automated Sentry page provides public access to the latest data on all known potentially hazardous near-Earth asteroids. This commitment to open information builds trust among nations and allows independent verification of threat assessments, preventing misinformation. The achievement of this international framework becomes apparent when compared to other global challenges. Nations that disagree on numerous matters find common ground in asteroid defense, recognizing that cosmic threats make no distinction between borders, ideologies, or economic systems. This cooperation may serve as a model for addressing other existential challenges facing humanity. As detection capabilities improve and more potentially hazardous objects are discovered, the International Planetary Defense System will face increasing demands. Current estimates suggest we've identified only about 30% of potentially hazardous objects in the 50 to 140 meter range. Expanding global collaboration will be essential to address this ongoing challenge. This international asteroid defense cooperation reveals humanity's capacity to overcome differences when facing shared threats. Political boundaries that dominate headlines fade in significance when confronted with the prospect of an asteroid impact. This cooperation represents both a practical necessity and a powerful demonstration of human solidarity for impact. In the face of international cooperation might help us deflect most asteroids, but the uncomfortable truth is that we need a backup plan. Within minutes of impact confirmation, authorities would divide affected regions into 3 distinct zones, and your location within them could determine whether you have hours, days, or weeks to prepare. The zoning system forms the backbone of asteroid emergency management. The immediate impact zone represents the area of certain destruction where evacuation is the only viable survival strategy. The secondary effects zone would experience severe damage but remain survivable with proper preparation. Buildings might collapse and fires would spread, but with the right precautions, people could survive. The tertiary zone would face disruptions to infrastructure and services, potentially for extended periods, requiring residents to be self-sufficient until help arrives. This three-tiered approach enables emergency managers to allocate resources effectively. For a 50-meter asteroid, experts recommend complete evacuation within a 50-kilometer radius from the predicted impact point. Beyond this, prepared shelters would be necessary within a 200-mile radius to protect from secondary effects like debris, shockwaves, and potential fires. Communities up to 500 miles away should prepare for significant service disruptions lasting weeks or months. The International Asteroid Warning Network coordinates these emergency responses alongside national and regional disaster agencies. Their protocols mirror those used for other natural disasters, but with modifications specific to asteroid impacts. The network ensures critical information flows seamlessly between scientific observers and emergency responders, providing communities with clear expectations. For those in the secondary and tertiary zones, survival depends heavily on preparation. Water purification methods become essential when municipal systems fail or become contaminated. Non-perishable food supplies should last weeks, as supply chains may be severely disrupted. Medical supplies need to account for injuries specific to impact scenarios, treatments for burns, respiratory issues from dust, and trauma care. Communication equipment, particularly battery-powered radios, becomes crucial when cellular networks and internet infrastructure collapse. The need for long-term self-sufficiency is emphasized due to the potential for widespread infrastructure damage and disruption of supply chains, notes a recent assessment from emergency planning experts. This marks a significant shift from typical natural disaster preparedness, which often assumes relief will arrive within days. After an asteroid impact, affected communities might need to sustain themselves for much longer periods. The impact location dramatically alters the preparation strategy. Ocean impacts create tsunami threats requiring entirely different evacuation protocols than land impacts. Coastal communities would need to move to higher ground, while those facing land impacts would focus on protection from debris and dust. The response to the 2011 Tohoku earthquake and tsunami offers valuable lessons, particularly regarding large-scale evacuations across extensive areas. What distinguishes asteroid impact preparation is the potential warning time. Unlike earthquakes that provide minimal notice, asteroid impacts might be predicted days, weeks, or even months in advance, if detection systems spot the object in time. This creates a scenario where authorities could potentially organize complete evacuations from threatened areas. The psychological dimension presents unique challenges. People may panic when confronted with such an extraordinary threat. Clear communication becomes vital, with authorities needing to provide specific, actionable instructions rather than vague warnings. Studies of public responses to tsunami warnings suggest that people respond best to concrete directives about where to go and what to bring. Asteroid impacts typically represent regional rather than global extinction threats. The 2013 Chelyabinsk event demonstrates this. A 20-meter asteroid created significant damage but remained localized. This shifts preparation from apocalyptic thinking to practical regional disaster management. Communities can survive these events with proper planning. Impact uncertainty zones create a unique challenge for officials. Unlike hurricanes with relatively predictable paths, asteroid impact corridors can stretch across continents. For Asteroid 2024 YR4, this corridor ran from the Eastern Pacific through South America, across Africa, into Bangladesh. Authorities must prepare communities along this entire path without knowing the exact impact location. Historical evacuation data from hurricanes and wildfires shows that many people choose to remain despite clear danger. Emergency planners must account for this when establishing shelters and stockpiling. Supplies. Communities outside the immediate impact zone would need to accommodate large numbers of evacuees for extended periods. Transportation quickly becomes a critical limiting factor in evacuation efforts. Major highways face gridlock as thousands flee simultaneously. Emergency planners advocate for staggered evacuations, prioritizing those closest to the predicted impact point. Public transportation would need to be maximized, with trains, buses, and military vehicles deployed to move people efficiently. Communication is vital during evacuation and preparation phases. Emergency broadcast systems must provide regular updates as impact predictions are refined. Battery-powered radios allow people to receive these updates even when power grids fail. Backup communication systems, including satellite phones and emergency radio networks, become lifelines for coordinating response efforts. Self-sufficiency represents the core principle of asteroid impact survival. Communities in secondary and tertiary zones should develop local resilience plans focused on maintaining essential services with minimal outside support. This includes community water purification, local food production, and distributed power generation through solar panels or generators. The most practical aspect of asteroid emergency preparation is its overlap with preparation for other disasters. The same supplies, evacuation routes, and community resilience strategies that help during hurricanes or earthquakes would prove valuable during an asteroid emergency. Communities can develop multi-hazard preparedness plans rather than treating asteroid impacts as a separate threat. Climate aftermath, long-term effects. Surviving the immediate chaos of an asteroid impact would be just the beginning of humanity's struggle. Even after the dust settles from evacuation efforts, a different kind of dust, millions of tons injected high into our atmosphere, could trigger climate changes more severe than any we've experienced in modern history. The climate aftermath of an asteroid strike represents a silent, secondary disaster that unfolds gradually, yet affects regions far beyond the impact zone. When a medium-sized asteroid like 2024 YR4 slams into Earth, the explosive force propels enormous quantities of pulverized rock, soil, and soot high into the stratosphere. Unlike volcanic dust, which typically remains in the lower atmosphere and washes out within weeks, impact-generated particles can reach altitudes of 30 to 50 kilometers, lingering for months or years. These suspended particles create what scientists call an impact winter, similar to the prolonged gloom following a catastrophic volcanic eruption, but potentially more severe. The physics is straightforward. Tiny particles absorb and scatter sunlight before reaching Earth's surface. For an asteroid the size of 2024 YR4, this cooling effect could reduce global temperatures by 1 to 2 degrees Celsius for several months, creating climate disruptions that ripple through ecosystems worldwide. The agricultural consequences of this temperature drop would be profound. Growing seasons would contract by weeks, with frost dates shifting unpredictably. Crops dependent on precise temperature ranges would suffer reduced yields or complete failure. The cooling would also alter precipitation patterns, causing droughts in some regions while triggering unusual rainfall in others. These disruptions would propagate through global food supply chains, potentially triggering shortages and price spikes thousands of miles from the impact site. The location of the asteroid strike dramatically influences the resulting climate effects. A land impact, particularly in areas with carbon-rich soils or forests, produces severe atmospheric dust loading as organic material vaporizes into soot particles highly effective at blocking sunlight. Ocean impacts generate devastating tsunamis, but might inject less dust into the upper atmosphere. However, they introduce different complications by vaporizing seawater and injecting massive amounts of water vapor into the atmosphere, altering weather systems through increased cloud formation and changed precipitation patterns. The atmospheric chemistry after an impact creates additional environmental hazards. The extreme heat triggers chemical reactions producing nitrogen oxides that combine with moisture to form nitric acid, a key component of acid rain. This acidification damages vegetation, contaminates freshwater supplies, and accelerates weathering of exposed structures. For recovering communities, these acid rains create new challenges, deteriorating building materials, contaminated emergency water supplies, and damaged vegetation crucial for food production and preventing soil erosion. The scope of climate effects scales directly with asteroid size. An object like 2024 YR4, while capable of destroying a city, would likely produce regional rather than global climate effects. The 1908 Tunguska event, caused by a comparable asteroid, flattened over 2,000 square kilometers of Siberian forest but produced minimal lasting climate effects due to relatively small dust ejection. In stark contrast, the Chicxulub impactor that contributed to the dinosaurs' extinction was approximately 10 kilometers in diameter, vastly larger than 2024 YR4. This massive asteroid ejected so much material that sunlight was blocked globally for years. Surface temperatures dropped by 10 degrees Celsius or more, creating a prolonged impact winter that collapsed food chains worldwide and contributed to the extinction of approximately 75% of all species on Earth. This scaling relationship between asteroid size and climate effects offers both reassurance and caution. While a 50 to 70 meter asteroid like 2024 YR4 wouldn't threaten human civilization through climate effects alone, these impacts would significantly complicate recovery efforts and could cause secondary humanitarian crises through food shortages and infrastructure failures. The asteroid's chemical composition adds another variable. Carbonaceous asteroids release different atmospheric contaminants than metallic or stony asteroids. Impactors containing significant quantities of sulfur, chlorine, or nitrogen compounds could produce more severe acid rain or atmospheric toxins, complicating recovery efforts further. Remote communities might experience these climate effects without understanding their cause. A small village facing unusual frosts, unexpected droughts, or acidic rainfall might not connect these phenomena to an asteroid impact thousands of miles away. This highlights the importance of global monitoring networks that can track and explain these climate changes as they unfold. Asteroid impact recovery planning must extend beyond immediate rescue efforts. Communities worldwide would need to adapt agricultural practices, implement water quality monitoring, and prepare for potential food shortages. Unlike immediate impact effects, which follow predictable physical laws, the climate aftermath introduces complex feedback loops in Earth's atmospheric systems. One concerning aspect is the potential to trigger cascading environmental effects. Cooling temperatures might shift ranges of disease vectors like mosquitoes, introducing illnesses to regions with no natural immunity. Marine ecosystems could face disruption from both temperature changes and ocean acidification, affecting fisheries and other resource-dependent industries. Despite these possibilities, modern technology offers advantages our ancestors lacked. Advanced climate modeling, agricultural monitoring systems, and interconnected food distribution networks provide tools to mitigate and adapt to these climate effects. Seed banks preserve genetic diversity for developing climate-resistant crops, while early warning systems for food insecurity can trigger preemptive aid before shortages become catastrophic. Throughout this journey, we've confronted a profound truth. Asteroid impacts represent one of the few existential threats for which humanity possesses viable solutions. The DART mission's success demonstrates we're active participants in cosmic affairs. International cooperation through IWN and SMPAG transcends geopolitical divisions when facing shared dangers. NASA's Planetary Defense Coordination Office advances our protective capabilities through the ENIO Surveyor Initiative. The 2029 Apophis flyby presents a crucial testing opportunity for our detection systems. We know another serious asteroid threat awaits. Our future safety depends on investing adequately in planetary defense today, turning cosmic uncertainty into manageable risk through science,